Okay, one more example problem for you guys. This is a bandwidth example, a little bit different than the one I did in class. So it's a very similar transfer function. So we have this transfer function right here. And to find the bandwidth of a system, we don't really care what having a forcing input is irrelevant to the bandwidth. The bandwidth is only a function of the mass of the spring and the damper. So the first thing to find a bandwidth problem is to figure out the damping ratio. So zeta is going to be it's c over 2 square root of mk. So we got 4 over 2 square root of 5 times 25, which is 125. That's going to give us a damping ratio of 0.179. And since it's less than 1 over square root of 2, therefore there is a peak. There is a peak. Okay, so let's talk about what this peak means, right? Remember, if we're looking at kind of like a frequency spectrum of sorts, so if we plot kind of like what our frequencies are, and we plot, say, magnitude ratios as a function of frequency. Remember, the magnitude ratio is the steady-state output is divided by the input force. So it's essentially proportional to the magnitude of the steady-state output. And as you speed it up, you're going to get some peak. You keep speeding it up, and it goes, whatever. And then it peaks at some frequency called the peak frequency, omega p. I noticed that I actually used the magnitude ratio as my y-axis, but I could have just as well done say displacement steady state divided by my static deflection, which is kind of like something I did in class, because those things are proportional. That's proportional to the magnitude ratio, so it's going to look the same. I mean, the scaling might be a little different, but all these different, you can plot a lot of. You can also plot straight up amplitude as a function of omega, and it will be a similar looking plot. It will have the same shape, just different scales. Okay, anyway, let's get back to bandwidth. So there's a peak, so we're going to use the equation, it's equation 4.2-9. It's the equation you would use when there is a peak. So we're going to use this equation. RBW is the square root of 1 minus 2 zeta squared plus minus 2 zeta square root of 1 minus zeta squared. And that's inside of that one. So obviously there's a plus and a minus, right? So we're going to do plus to get the upper limit, and then we're going to do minus to do the lower limit. So let's find the upper limit first. So R bandwidth upper, a lot of subscripts there. And I'm just going to basically evaluate it with the zeta that we already calculated. So it's going to be 1 minus 2 times 0.179 squared. So the first one I'm going to do is plus 2 times 0.179 square root. I got to really extend this guy over here. 1 minus 0.179. So do the calculation. What you're going to get you're going to end up with RBW upper is equal to, I have it here somewhere. 1.135. 1.135. All right, so from that we find our upper bandwidth frequency, and remember that R is omega over omega n, right? So in other words, my omega bandwidth upper, which is the input frequency, upper bandwidth input frequency, is basically going to be this R BW upper times my omega n. So let's find out omega n real quick. Natural frequency is going to be the square root of k over m, which is the square root of 25 over 5, right? Which is the square root of, just the square root of 5. So omega n in this example is 2.24 radians per second. Alright, just put this kind of on the side. So what do we got? Let's go up. So my bandwidth upper frequency then is going to be 1.135 times 2.24. and that's going to be equal to 2.54 radians per second. All right, we have the upper. Let's find the lower. So we're going to do the opposite of that. It's going to be RBW lower. It's going to be the square root, and it's going to be a very similar equation, except we're going to use a minus. So 1 minus 2, 0.179 squared. Now we're going to use minus to find the lower one. 2 times 0.179 square root of 1 minus, being a little sloppy with my writing here. Okay, and then that's going to give you a lower bandwidth R of 0.764. So then obviously the lower bandwidth frequency is going to be this RBW lower times the natural frequency. So you end up with 1.71 radians per second. So basically we have our answer. My bandwidth, omega BW, is basically between 1.71 and 2.54 radians per second. And you know, it's a good time to do a quick reality check, right? Because notice that what this means is that we have basically our, magnitude ratio over omega. You have a peak, right? And the way we're defining bandwidth is kind of like encompassed by this, this is the peak magnitude ratio. This is 1 over square root of 2 of MP. So the bandwidth is going to happen at these two frequencies. So we found the upper one to be 2.54, the lower one to be 1.71, and notice that the peak frequency is going to be somewhere in the middle. It's a good idea to find that peak frequency just to do a quick reality check, and we know that's going to be omega n times the square root of 1 minus 2 zeta squared. I gave you that. If you plug in omega n and zeta squared, you're going to find here that omega p is going to be 2.16 radians per second. And if you look at the numbers, 2.16, it's going to be right in between the two that we found. So it checks out. It's good. I'm happy. I'm good. All right.